Intro to AWS. So in case you weren't aware, AWS is a cloud provider. They're a pretty big one. If you look at the whole Gartner Magic Quadrant thing, they're kind of up in the right-hand corner, which is always good. That's why we love them. We have built on Azure. We've built on GCP. All good cloud providers. Hard to match up with what AWS offers nowadays. So, what is AWS? Their nice tagline here, AWS provides highly reliable, scalable, low-cost infrastructure. Millions of businesses, 190 countries around the world. Basically, they have it all. So, the old days of provisioning things up front, paying a lot up front for machines that we may or may not use are gone. The idea is that you just pay for what you use, you provision it when you need it, you deprovision it when you don't need it. That's what gets you that elasticity and agility. So, even if you're building, say, a website and you need to be able to handle users and the influx throughout the day, building a system so that it can handle that influx and scale down and scale up throughout the day is key. It's open and flexible. Basically, you can do anything you want on it. I've been building on it for 6 years now, and I have yet to find something that I can't build using AWS. It's super secure. We get into this a lot, especially when we're dealing with HIPAA workloads and things that involve PCI compliance. It checks all the boxes. We don't need to worry about that. They have it taken care of, and it's got this giant global reach, so they're everywhere. So throughout this thing, we're going to be doing a little bit of polling just to get some feedback. These aren't anything, too intensive. They're meant to just kind of spark some conversation a little bit. So what you'll see is I am going to launch a poll, and hopefully everybody sees it. Some of them are more about your background and experience and what you would like to see. Some of them are more like this, where it's, hey, do you know anything about AWS? It's more of a trivia question. And we'll see what people come up with. I won't wait for everybody. I'll revisit this in a few slides to see what everybody kind of weighs in on. I'll keep going with the AWS stuff here. So AWS, basically, I just want to give a very basic overview of some of the core concepts of AWS, just so that everybody's on the same page. I know some people on this call might be well aware of these things. Some people might not have no idea, but we'll just cover them very briefly so that everybody's level-setted. So AWS has this concept of a region, and a region is literally a geographic region where they put what they call availability zones. So, a lot of us in this area, we're going to be operating out of the West Virginia, or just the Virginia region, basically. Some people will operate out of Ohio. In the United States, there's a few others. There's Oregon, there's Northern California, Canada. There's one region in Canada. But basically, this geographical region is composed of what they call availability zones. An availability zone can be thought of as a data center, but it's actually composed of one or more data centers. They put a hard cap on how large their data centers are just from a manageability perspective. These availability zones, usually when you are architecting a software system on AWS, you want to make it so that you're spanning multiple of these. And this is what gives you that high availability that we always talk about. Within an AZ, basically, because these are comprised of multiple data centers, we need to be able to talk across them very, very quickly. The key to this is the infrastructure that AWS has built in place. So within the AZ, there are lines communicating between every single data center. There's lines communicating between every single AZ. And then there's lines communicating out through whatever other regions are available. If we look at kind of their global footprint, we can see basically there's 22 regions currently, with 5 regions coming in the future. Things like Spain, Jakarta, Cape Town, Milan, Japan. All of those hosting 3 or more availability zones. There's a bunch of CloudFront POPs. So if you know anything about content delivery networks, they've got a product called CloudFront, which is their CDN. They have over 216 POPs. I think that this number is a little outdated at this point. These are super useful because they're effectively their edge locations. And that's where we want to push content out to users. And that makes basically serving content to them that much faster. And then there's this concept of direct connect, basically a line that you have directly into the AWS backbone. If we look at this, this is basically their transcontinental connection of wires. Not going to dive too much into it, but everything that they build is operated and owned by them. And that puts them at a unique advantage because they have complete control over everything that they're doing, and they can actually make their SLAs that much higher because they have that ability. So AWS is great, blah, blah, blah. I'm not going to go into more detail on that. Really, we want to talk about what is a data lake. And I'll look at the poll here for a second. So the first service launched by AWS, we had the majority saying S3, which is correct. Some people picked SQS, which is almost correct. Technically, it was the first service built. However, it was before they actually made AWS as its own entity. S3 came shortly after, and then EC2 was a close third. SimpleDB, a product that is no longer even around, is something that I think I used for a couple months, and then all of a sudden it just disappeared. I'm not really sure when they made that one, to be honest. But back to a data lake. So what is a data lake? Why do we want one? How is this useful for machine learning and artificial intelligence? All great questions that we would love to answer. So what is a data lake? Well, if we look at the strict definition, they say it's a centralized repository for both structured and unstructured data. Basically, you can store the data as it is in open source file formats. So this could be, you could be storing just text files. You could be storing them as CSVs, JSON, whatever. You could be storing zipped up files, Parquet files, anything that you want. We just put it on the data lake and it's available for direct analysis. Now, saying that a data lake is a centralized repository for structured and unstructured data is correct, but it's not exactly useful, I'll say. So even though I've been in the AWS space for a while now, and I've been building on it for a while, a few years ago when this whole concept came about, I still didn't really understand it. I didn't understand what exactly it was. It seemed like this interesting concept, but it wasn't concrete enough for me to wrap my head around. And me in particular, I was very used to the data warehouse world. So I had this massive relational database that was used for one thing or another. And that's where I thought, that's where all my data came in. That's where I did all my analytics. Why would I need this data lake? So, we have to ask the question, why a data lake? One of the main ideas here, though, is we want to decouple storage from compute, because that's going to be what allows us to scale. So one thing about the data warehouse that is nice is that I have this immense amount of power, this immense amount of compute power to do all these analytics that I want to be able to do. But to some extent, compute and storage are always kind of tied together. So for example, if I'm using, say, Redshift, which is AWS data warehousing solution, it's great. It's one of my favorite products. I love it. But to keep that thing running, I pay per storage per node. And if I want to increase the amount of storage, then I have to increase the amount of nodes, basically increase the amount of compute, which makes logical sense because as I have more data, I need more compute to handle that. But it's not always running all the time, and I don't necessarily need all the data that's in my data warehouse all the time. And that's where it becomes very important to be able to decouple those two things so that I can only pay for storage all the time because I need to store that data, but I only pay for compute when I need to process that data. So the next point is, it enables advanced analytics across all your data sources. So because this can house any sort of data, whether it's flat files, whether it's backups, whether it's JSON data, I can handle it and I can query across those. Long gone are the days of where, oh, this isn't in my data warehouse, it wasn't in a relational model, I can't do anything with it. Now I can take all this data in from, whether it's not, I could export my data out of my data warehouse. I could have data coming from different relational databases. they could all go into my data lake, and I can query across all those data sets, which gives me a lot of powerful things like gaining different insights. I can basically reduce the complexity in ETL because it's not tied directly to my analytical compute engine. It's not tied to whatever relational database I have running under the hood. And it's very extensible because I don't care what the data is. Just throw it in there and I'll sort it out and I'll figure it out later so I can query across it later. So traditionally, this is kind of what our analytics look like. We had basically a whole bunch of different systems, OLTP systems, ERP systems, and they all fed into a data warehouse. And that works because they were all relational models. And then we'd go into our data warehouse, we'd run some sort of ETL process, and that was all great. The problem with that, though, is the data warehouses were able to handle a lot, but they were on the scale of like terabytes to petabytes. And I always needed to have that schema defined before I loaded that data in. So if I added a new data source, say I added another OLTP data source, I needed to make sure that I had a schema that was compatible with that before I loaded it into it. Everything was there, but it took a lot of time and effort to get it there. So there was also a large CapEx here because I had to pay for that capacity going forward, even though I might have to pay for overhead because I know that I might use it now down the line, but I'm still paying for it now. So now instead, we've kind of got this approach where it looks similar. So I've still got kind of all these different data sources like my OLTP data sources, ERP and CRMs, but I can also get data from devices, IoT, web, different sensors. I can take feeds from different social platforms like Twitter or Facebook. All that data can be stored at a very minimal cost compared to what I was paying for a data warehouse. And this scales almost infinitely. Here we're talking, not terabytes to petabytes, but terabytes to exabytes. This is required when we're talking about the kind of internet that we're used to today. So now that we've got all that data in one place, it doesn't necessarily have to be the same form. It can be relational data, but it doesn't have to be. And I don't necessarily have to pay for the compute, even though I'm storing it 24/7. We'll get into this idea of schema on read as opposed to schema on write, which is what we're used to in the data warehouse. And then we have all these set of tools, these different analytics engines that we can use against our data our data lake that might not have been applicable when we were in the data warehouse world. So, before we kind of always had this problem of, where is the data? It's distributed in all these different systems. And they were distributed in these different systems for good reason, because typically when you're designing a software system, you want to maintain control of the data source along with the application that's using that data source. And you want the data that's in that data source to only be applicable to that because you're going to minimize the amount of replication that you're dealing with there. But there's no reason we can't still have that. We can still have those systems that all contain their own data, but we can also offload that to our data lake. So we can store and analyze all that data in a separate place and not impact the underlying system. Again, we get back to how do we scale this? If I've got this vast amount of storage, how can I be able to scale my underlying data storage as the volume increases, especially when we're talking about the modern internet and social feeds and IoT data. So the way that we can do that is just by decoupling that compute and decouple that storage. That way we don't always have to be paying for that compute, which is expensive nowadays. That's going to be the choking point. The other major problem half the time with data warehouses was the fact that getting that data in could be troublesome. If that was a relational database, we probably could define some ETL process that would allow us to export the data maybe into a CSV format and then import it into our data warehouse. But what about all that data that didn't abide by that format? What about that JSON data? Maybe whatever technology we were using didn't support JSON at the time. It's been difficult to find an upgrade path to get to the point where it can. What if it's just made in a different format? Maybe it's in Parquet format. What am I going to do with that if I got to load it into an Oracle database? So with a data lake, though, we can ingest anything. We don't care. It's just a flat file store. We just throw data at it and we figure out what the schema is later. So then schema on read, before we had schema on write, if I needed to ingest data, I needed to have a table there. So I needed to define my schema before I actually put the data in there. And that was a very labor intensive process of figuring out what that was. And then now I can just take anything. I can do that data or that schema on read and then do analytics on it at runtime. So, I think that talking about these concepts is good, but it doesn't make any sense unless it's actually usable in the real world. And I think that, at this point, we've had enough success with different companies that, we've proven out that it is effective. It is a good strategy. Centimark, we've been working with them to build the data lake because they've got multiple different applications that all have their data stores, but it's very hard for them to get a holistic look at how their business is working across all these different aspects. And I think that a lot of companies face the same issue. Transcat, for example, we're building a data lake to solve pretty much a same issue here. We don't know, they have 7 or 8 different data stores that all contain different data, and that's all good. Those data stores provide a very specific purpose, but what if I want to get a more holistic view of how my business is doing across all these different verticals? That's where a data lake comes in. I can dump all that data, export it out into a data lake, and then run ETL and analytics on that. Virtual moving technologies, they're really cool because they're using machine learning to be able to help with their ability to quote moving different people. So before, they would have to, people would take their camera phone and they take pictures of their house and they would send it to VMT, and they would actually have people looking through these and say, okay, well, there's a couch, there's a table, this costs that, this costs that. But these are all things that we can use machine learning to do. We don't need to have people doing it anymore. So instead, we work with them to build a data lake so that you can take these pictures, you can upload it to their site. We'll run it through these algorithms and we'll identify that, oh, there's a couch, there's a table, it costs this much. We also need to know that, oh, well, that's a window, we don't want to move that. And they found that not only are they decreasing the amount of people that need to be on staff to handle this stuff, they've actually found that their quotes are, I think before their quotes were like 70% accurate, and now they're finding that their quotes are more like 85% accurate. So all these cases, start building up this idea that, okay, a data lake is the next thing, and it is actually, viable and it's useful. So how do we build a data lake on AWS? Because these are all concepts. Well, why AWS? AWS is a million different tools, basically. And they all serve a specific purpose. So if we kind of get the chance to pick and choose what we want to get the result that we want. If we look at kind of what a data lake looks like on AWS, we get a picture like this. And this is kind of like the poster child for a AWS data lake. So first of all, S3 is kind of the center of our world. S3 is just an object store. It is infinitely scalable. It's highly available. And there's a million ways to get data into AWS. So in this case, we've got various types of data ingestion. We've got Snowball, which is just a physical device that I could hook up to my computer, load data on it, and I could literally ship it to AWS, and they're going to put it on S3. I've got Kinesis, which is like real-time data streaming. So think about IoT devices. I've got all this data coming off of these devices. I can effectively just batch all that data and then put it as a flat file onto S3. And then there's other things like Direct Connect, having a direct line into AWS, database migration service. This is probably a very common use case because everybody has existing databases that they want to get the data into AWS. And then storage gateway. Basically, I can effectively mount a drive locally that exposes it to S3. Catalog and search, I'll explain why these are so important. Without these types of things, instead of a data lake, we start to get what they call a data swamp. Having all this data is not terribly useful if I don't know what data I have. Access and user interfaces, I won't go into this too much. These are kind of cross-cutting concerns as far as AWS goes. All these controls are in place in AWS and they apply to the data lake as well. Manage and secure, same thing. You can meet any sort of compliance needs that you have with AWS and with a data lake. But then analytics and serving, these are the things that we're going to also be talking about. What are some of these awesome high-level AI services that AWS is offering? How can we actually use the data on S3 to get some sort of insight out of it? So I have another poll. Launch that. Then we'll revisit that in a few minutes. Okay. So, I talked a little bit about how S3 is kind of the center of our universe when we're talking about a data lake on AWS, and why is that? It really comes down to these 6 main points. So it's durable. So it's designed for 11 nines durability, which is effectively saying that if you put a file on there, you're not going to lose the file. It's highly available. It's designed for 99.99% availability. So at any given time, you can almost guarantee that it is up and it is available and I can use it. It's very high performance. It's amazing the engineering that's gone under the hood for this. It's easy to use. It's got REST APIs. It's got SDKs attached to it. You've got event notification and different life cycles. So I can age things off from the hot storage tier of S3 to infrequent access or archival storage if I want to pay less. It's scalable. Basically, you do not need to worry about scaling it. You just throw files at it and it will scale for you. You're never going to really run into a hard cap. And then it's integrated, which is a very important point when it comes to building tooling on AWS. All these other AWS services are there, and almost all of them natively integrate with S3. So what are some of the things that I can do with a data lake? So there's something called Amazon Athena, which is basically a way to query flat files that reside on S3 using ANSI SQL. And I'm guessing that a lot of us that are used to the old world of having data warehouses or just having databases, we're used to having some sort of IDE that looks a lot like this. So this starts to get you a little bit more familiar in the new world of the data lake. We can use Hadoop and Amazon EMR to run analytics. So you can see here we're defining different processes that we can then look at with Zeppelin. We can use QuickSight, which is basically AWS's BI tool, so we can create nice visualizations. I know that I've had to build a number of platforms that kind of do this stuff ad hoc to create nice graphs and pretty pictures. But with QuickSight integrating natively into AWS, we can get it out of the box. And then, applicable here, we can train ML models with Amazon SageMaker. So this is, really the reason that we're having this this chat today. How can we actually leverage a data lake to get to this point? And then we can kind of have our central data catalog with Glue. We'll talk more about this coming up, but this is going to be very important because, again, if I don't know what data I have, then my data is useless. And then I can load into Downstream Services. So, one thing that I'll note that I'll probably talk more about later is that, S3 is amazing for storing that data, but that's not necessarily where you want to do your analytics. So instead, I could take all the data that I have on S3 and load it into a service that's actually meant for that, whether that's Redshift or Aurora. If I've groomed it so that I just want to serve it as like an API call, then I can use something like DynamoDB or Elasticsearch. So we'll talk about like how we actually go about working in a data lake. So with the poll, I asked, have you built any data warehousing type environments? So we have a couple of people that have actually done it in AWS. Had a few people that have done it in on-premise environments. Looks like most people probably haven't built data warehousing applications. That's okay. You're probably better off. You feel accomplished when you get done, but it's not fun all the time. So working in a data lake, we've kind of got all these constructs around. We've got S3, we've got all these different services, but how do we use those services to get what we need? So we're going to talk a little bit about optimizing for cost and performance. We'll talk a bit about how we actually catalog the data that we have in S3 using AWS Glue. We're also going to talk about using Glue to transform the data, how it has that ability to do ETL, how we can then actually query that data on Athena and then visualize it using QuickSight. And again, these are all kind of like precursors. So, you know, the whole point of this conversation is to talk about AI and ML with AWS. And these are really just precursors. How do I get this data into the format that I need so that I can create these models? So again, if we look at our, you know, favorite picture here, what we're really concerned with right here is this data ingestion, this catalog and search box. Getting data in, and more importantly, how do we actually catalog it? So, you know, in order to kind of progress further, we really need to look at cost of performance. So all these things are based around a consumption model. The nice thing about these services is that they're what we consider serverless. I talked in the beginning about AWS and how it's got these concepts of regions and availability zones and how you architect for providing high availability. You know, and with a lot of these services, you can kind of throw that out the window, to be honest. So, you know, if I'm just building a regular application and I've got to have some machine hosting some, you know, web server, then yeah, I am concerned about the fact that I need to span multiple availability zones in case something goes down or something goes wrong. But these are all serverless solutions. So there's nothing for me to manage. It's all managed by AWS under the hood. So even though those concepts exist, I don't need to worry about them. But because of that, the pricing model has changed a little bit. You pay for what you use, and you pay for how much you query and how much you store. So we really start to, you know, that's where it becomes important to look at optimizing for cost of performance. And how we do that is looking at partitioning. We look at how we can compress things, and then looking at using as many managed services as we can. So with partitioning, say we've got a structure like this. So on the left hand, we've got a bucket in S3. And a bucket is basically just a place, a division of place to put files. And you can see that I've got a bunch of gzipped, tar gzipped files in here. They appear to be ordered by some sort of date. It looks like there's some kind of country code in there a little bit. Now, if I wanted to query that using Athena, what would end up happening is I would end up scanning every single one of those files to look at the individual records that are in those files. So that could be a lot of data. However, if I move to a model more like on the right, where I structure it, where I actually have key prefixes within my bucket and I store those files within each key prefix, then I get proper partitioning. So if I run the query on the bottom here, select star from my data lake, where the date time is that and the country equals US, you know, on the left-hand side, I need to scan every single one of those files. However, if I can organize them a little bit more intuitively, and I can organize them so I, you know, do them based on date time and then based on country, when I run that query, I only need to look at a single file. So what are the advantages of that? So on the left hand of this, table, you can see where I ran that query against a non-partition and partition table. Think about the very last example. In the non-partition version, if I run that query, it's going to come out to just under 10 seconds. Not terrible if I'm just looking to do a little bit of discovery, but not great. The biggest pointer, though, is that if I do that on the non-partition side, I end up scanning almost 75 gigabytes of data. And with the cost modeling of consumption based on these serverless resources, that means that I'm going to pay 36 cents to run that query. Now, that's not a lot of money, but it's not trivial, especially if I'm going to be doing a lot of those queries. Versus if I actually partition my data correctly, I end up scanning only 29 megabytes of it, which comes out to a fraction of a penny. On the right-hand side, it's a very similar scenario. I'm not going to walk through it, but it's basically doing that same thing except across the date range. Again, you're going to scan all the data versus a much smaller subset of that data, resulting in 36 cents versus 0.004 of a dollar. So then we have to look at compression because we pay for the amount of data that we store on S3. So it's obviously advantageous for us to compress it so we store as little as possible. Not only is it going to make you pay less, but it's going to end up speeding up your queries. And this is there's a little bit of a caveat here that we'll go into, but we get an example of this looking at different algorithms, whether or not they're splittable, meaning that if I've got a single file, can I concurrently read multiple parts of that file? And then it just does a comparison of the compression ratio, the algorithm speed, and what it's really good for. So we've kind of got just like gzipped files, which are very common. It's good for raw storage. On the other hand, if we go to the bottom where we've got something that's snappy compressed, this is going to be good for a wide range of things, slow and fast analytics. So snappy is a great compression method, and it's also splittable, which means that I can store a large chunk of data as one file and still be able to read that file very quickly because I can concurrently do it. So another poll. Oh, and polling. So for anybody that's ever heard of Snappy before, maybe you can answer this, or maybe you're just quick enough to Google it, but we'll see. So here is an example of compression. So if I just had a raw flat text file sitting on S3 that was 1.15 terabytes, and I just wanted to run a select star on that file using Athena, what that would amount to is basically, just under a 4-minute runtime, which is excruciating. But we would have scanned all 1.15 terabytes of that. Now that's pretty significant because for me to run that one query, that just cost me almost $6. Whereas if I use something like Parquet, which by the way, under the hood also uses Snappy, the size of it sitting on S3 is 130 gigabytes. So my runtime ends up being less than 7 seconds, and I only scan 2.5 gigabytes of it. So I only paid just over a penny to run that query. So again, we want to keep in mind compression and partitioning when it comes to our data lake, because that's going to save us a lot of time. It's going to save us a lot of money.
Hey, Dustin, we have an audience question in the chat box if you have a second to answer. Can you expand slightly on the concept of splittable and concurrency?
Yes. Is it this one? Okay, so that's actually a great segue into what this slide is. So it's a little counterintuitive because one might usually think that I want to, if I'm storing all my files, I'm storing all my data on S3, it would be advantageous to store them as a lot of very small files across maybe different partitions. The upside of that is that, okay, I can naturally concurrently read those, right? I've got many different files. Athena has the concept of readers. I can have many readers when I issue a command. So if I need to run some statement, I can have all these different readers go out and read all these different files. The kind of counterpoint to that, though, is the fact that we are dealing with network here. This process isn't running on S3. It's running against S3. So we have to deal with the network latency involved with reading each and every single one of those files, as well as the metadata that's stored over top of those that's included on every single one of those files. Versus if I've got a splittable format like Snappy, it's very interesting because I can actually use multiple readers on a single file. So I can end up pulling that file once and only once, and I can read through it in parallel to end up getting the results that I need. And it actually even points out here, you actually end up getting faster listing operations. So in this case, we're talking about fewer larger files is better than smaller files. So if you look at the top one, select count star from our data lake, say we've got 5,000 files. It's going to take about 8.4 seconds to run that. Of course, these are all a little bit made up because we don't know the size of the files or anything like that. But on the other end of that, if we have one single file and we select from that one file, we're going to get 2.31 seconds. Now, it's important, though, that the file can be splittable, because if I can only use one reader on it at a time, then I'm going to come out with a very similar number. So that's why we always want to try to use file formats that are inherently splittable. So, those were just kind of some I guess I'll call them ground rules as far as how we want to store data on S3 in our data lake. What we're kind of leading up to though is this, cataloging and transforming data. So AWS Glue is a service that really helps bring that manageability aspect of our data lake to life. Because if I've got all this data sitting on S3, great, I know that I have some amount of data, some type of data, but I don't know what I have, how to access it, where it is. So, you know, ETL in the past, a lot of it has been hand-coded. Take it from somebody that's had to write many different ETL processes. It is good because, like they say here, it's flexible. It's very powerful because you can make it do whatever you want. Because you are the one actually writing the code, you can wrap it with unit tests, you can do CI/CD, but it's very bad because even though you try to make it as generic as possible, it tends to be brittle and error prone. It tends to only solve the problem that you were thinking of at the time. It takes a lot of time. It's very laborious. The source of the files that you're dealing with changes unbeknownst to you. The schemas that you're given changes, the volume that you're given changes. Maybe you just didn't architect it appropriately to handle the amount of volume that you're getting now. Everything always changes, and that's a problem if you're developing your own ETL. So instead, AWS came out with Glue, which basically has three aspects to it. There's a discover portion of it, which is basically a way to catalog data, which is very important when I'm looking at storing a ton of data on S3. It allows me to develop different ETL processes on top of it. And then it allows me to actually, once I've created those ETL processes, deploy it in the wild so that I can use them in a production workload. So if we look at the different components, the first one is the data catalog. This is kind of what it looks like. So as you can see here, you know, I've got basically a list of tables that are part of a database. And if you look, you can see, you know, what database they're part of, what their location is. So obviously, a lot of the times we're dealing with files on S3, so we can actually see what the underlying files that comprise that table are. We can look at the different classifications of them. So for example, in this case, we're looking at some CSV data. We're looking at a file that's in Parquet, some last updated time. So this is very important to me because I need to know these things in order to create any sort of meaningful insight about the data that I have. And it can handle a lot more than just S3. So the Glue data catalog, where I would basically have these databases, have these tables defined within the database, they're usable by Glue, they're usable by Athena, they're usable by Redshift Spectrum, which is, I talked about Redshift, which is their data warehousing option. Spectrum is basically the ability for Redshift to end up using the Glue catalog to query data on S3, which gives a whole new set of possibilities for your data warehousing application, because perhaps there are some files that are literally just too large for you to fit as part of your data warehouse when you have other maybe customer data that you need to load into it. I can still use that data by querying it on S3, and I can join it against the data that I have in the warehouse. And then it's also integrated with EMR, which is basically AWS's Hadoop, managed Hadoop and Spark environment. But just as importantly, there's this concept called a crawler. So we talk about schema on read, and this is effectively what enables that. So if I didn't have this idea of schema on read, then I'm not a whole lot better off than my data warehousing solution. Any new data that's coming in, I still need to go and figure out what the schema is. I need to provision that table. I need to make sure that it loads correctly. Make sure that maybe any types that are mismatched can align. But instead, I have a data lake. I want to be able to just dump data in here and then sort it out later. And the crawler is what's going to allow us to do that. So, the crawler will basically go against the any S3 path. It will detect the file type. It'll extract the schema from the underlying files, and it will automatically do that partitioning that I was talking about before. So if I have already structured things in a way that allows me to more specifically query data on S3, Glue will automatically create a table that utilizes that partition under the hood. There's a couple of ways that you can actually run the crawler. So it could be on demand or scheduled, which I think is a little funny because if you can do it event-based, and why they separate those into scheduling on demand, I don't know, because they're both events. But and then the last point, they point out Grok. You can basically create your own classifier. So for example, if I want to classify something, I run it against a file in S3, it comes back and it says, oh, this is a JSON file. But perhaps there's a completely different type of file that AWS has not prepared this for. You can use Grok, which is basically a pattern matching syntax, to create your own classifier to handle that if you really need to. So far, honestly, in my time dealing with data lakes, I have yet to find a file that's not in those typical formats, but it's useful if you need it. So the crawler can actually go against more than S3 though. So I can stick it against RDS, which is the AWS Relational Database Service. So this is, I need a database, but I don't necessarily want to manage creating, patching, all the other things around the server that would be hosting the database. So I could have MySQL databases, MariaDB, Postgres, Aurora, which is a different flavor of these. But it can run against all those. It can run against the Amazon Redshift product. And then of course it can run against the NES3 bucket. So I can look at and figure out all those different types of files that you see there on the right. All right, one other poll. I don't know if I went over the last poll. All right. So, just to reiterate, this is kind of what the Glue data catalog looks like. And it's going to bring in the metadata from all my different data sources that I'm working with. That way I have a very holistic view of what I have available. And you can see here, some of these are S3 paths. I have some of them that are Redshift, some that are Postgres, a variety of different things. I need, I want to be able to query across all these different environments to be able to create new types of data sets. This is kind of what it looks like if I were to inspect an individual table. So you can see at the top that I've got different properties about the table itself. Things as simple as the name and the database that it belongs to, the location on S3 that it might lie. I've got different statistics about the data that comprises that table. So the key size, the number of records that are involved. I've got what's the classification, if it's CSV. And then I've got what the table schema is. And this can be, these table schemas don't necessarily have to be flat. They can be nested. I could have different structs as it shows here. I could have this user attribute, maybe this is a JSON file, and that user attribute has a bunch of different aspects underneath it. So it can handle that as well. So what do Redshift and Parquet have in common? Looks like majority is correct. They are both a columnar format. I think that that's kind of the new wave of data warehousing. Redshift did it. Redshift is actually based on a fork of Postgres. It was a product actually bought by AWS many years ago. I forget the company name that made it, but it was really a revolutionary idea. And they really ran with it. And even internally, I think there's, now I'm trying to think. I remember when I was doing a lot of development on Redshift, I kept coming across errors that referenced like some of the underlying C source files. And it was, I remember looking at why they were named that way, and it turns out it was the original name of the Redshift product, and it was something like Mickey Mouse. That's what their internal name for Redshift was before they actually released it to the public. But I wanted to post that in the trivia too, but I knew nobody would get it. So The crawler, so detecting schemas and partitions. So, it has this capability to, catalog the data for us. But one of the really nice things about it is if I've got a conceptual table in AWS Glue that doesn't necessarily correspond to a single file in S3. So what I want the crawler to be able to do, and what it does, is it will actually examine multiple, the similarity across multiple files within a key prefix on S3 to determine if they should be considered as part of a single table. And they'll do that based on the columns, they'll do that based on the types, and it will actually walk the structure up the S3 prefixes to the root of the bucket to figure out what should be grouped together. This is kind of just showing what the automatic partition detection is. So the partitions are effectively going to be the key prefixes within S3. And if it determines that those are appropriate, as you see here, we can see that it will offer those as effectively attributes of the table. So I can query them just as if they were any other column within my table. So, once we've cataloged our data, really we want to do some sort of ETL process on it. Basically, we want to prepare it or begin writing an ETL process that will prepare it for whatever machine learning or AI use case that we want past that point. So this is kind of a walkthrough of what that would look like in AWS Glue. So the first thing that I would want to do is pick where my source is coming from, what table that I want to target, whether that's in S3 or it's in a relational database or Redshift or Dynamo. Then I'm going to pick my target. Where do I want the results of my ETL process to go? Pretty simple. I want to pick my source, and then I want to pick my target. Most of the time, that target's probably going to be another S3 file. And then I want to do some sort of ETL on it, whether it's as simple as what you see here, where maybe I just want to remap some columns or rename or drop some. Or I can, basically by doing this, what's going to end up happening is it's going to generate a template for me of actual Python Spark code that I can then go in and edit to do much more interesting things. So, it gets rid of a lot of that boilerplate that I would typically have to do on any given ETL process, just by letting me choose a few things from the UI and then letting me go in and do whatever business logic is more appropriate. This is kind of just an example about some of the code that it generates. It's just editable, portable PySpark and Scala code. So this could be generated as Python, basically PySpark code, or it can use Scala, which I don't know if anybody's familiar with Scala. It's kind of a Java derivative. And then, of course, my ability to do more custom things might also be dependent on my ability to get outside libraries. So in this case, I could direct it towards the path of a different Python library file. If this is Scala, I could put in dependent jars. Or if there's just other external files, maybe I need them for some sort of environment variables or credentials, I can just include different reference files. So then once I run this is going to run on Apache Spark. Spark is basically a parallel, horizontally scalable data processing engine. In AWS, it's completely fault tolerant. It's built in. It's a managed service, and it's flexible. So I can either use Python, I can use SQL. It's got this huge ecosystem around it. So Apache Spark has been around a lot longer than it's been used in AWS. So there's a lot of tooling built around this. And then the AWS Glue ETL libraries are basically just nice pre-packaged pieces that you can pull off the shelf to do a lot of the different workload things that we would need in an ETL transform. So, these are just a couple of examples of some of them. So the resolve choice, right? I have something that is comprised of two entities. Maybe I want to project it to only be one of them. Maybe I want to cast it into a certain way. I could separate that one column into multiple columns. The apply mapping, for example, say I've got this nested structure here. I'm dealing with JSON data and I want to be able to flatten it out in some manner. Then I could transform that into what you see on the right. And then there's a bunch of these that are built in. And obviously, I'm not going to go through all of them. I'm only going to go through the 2 that I did. But there's a handful of these that Glue already has off the shelf that I can just kind of pick and choose to build the ETL that I need. It's also got this concept of a spigot, which is really convenient because say I'm doing the development on this, I might need some sort of test data. The spigot can be used to actually just throw random data at it. Then finally, the last part of this is job execution. So, we've created this ETL process. Now I actually want to execute it. It's one thing to be able to write it. It's another thing to be able to execute it. AWS Glue has its own orchestration where I can set up, different pipelines of how I want my workflow to go. Maybe it's just as simple as it's a single job and it runs, it transforms, it puts a file in S3. Great, you're golden. Or I can just get a lot more complex where it's event-based. Maybe I've got different steps in my workflow. Maybe I've got different ETL processes that I want to run one after another. And of course, these can be scheduled, event, or on-demand based. So for example, maybe I am constantly uploading new data to some bucket in S3. I could have that trigger an event so that it could go and maybe trigger my crawler and then trigger my Glue ETL process. As I would expect with any sort of ETL tooling, it has kind of job metrics that allow me to see various aspects of it, like runtime, how much time is idle, what it's spent in queue, how much data it's processed. I can see progress in history. These are things that I would just expect out of the box from an ETL process because they are must-haves. And of course, just like I was talking about with S3, this is serverless. So there's nothing for you to manage. You don't have to provision services. You don't have to worry about high availability. All of that stuff is taken care of for you. So, it's nice to be able to write these ETL processes. Just reading the comments here. So yeah, I mean, all of this stuff being serverless, it's strictly pay as you go. So if my Glue process is running, then I'm getting billed. If it's not running, then I'm not getting billed. So if I can make my process as efficient as possible in terms of runtime, then I'm going to be better off. And that doesn't matter if it's development or production. Obviously in production, you're typically going to have higher run rates because you might just constantly be ingesting data. But the billing strategy is always going to be the same with all of these serverless resources. So if we want to just query the data, which is very important, especially coming from somebody that had a data warehousing background, even though I've just ingested data, maybe I've got it to match my schema, I don't necessarily know what the data is telling me. I could have a name field, but for all I know, there could be garbage in it and it might not actually be a name. So it's important for me to be able to ad hoc query the data. So, why would I want to query it? Again, I've got new data sources and I want to see what the new fields that I have available to me are. I might want to, maybe I'm ingesting log data and I want to interrogate the logs. Maybe I want to do some very light analytics. Generally if I'm just doing ad hoc querying, I might do some small amount of analytics, but I'm not going to do any heavy aggregations. I might want to look at relationships across sets. Maybe I have existing data that I want to see if it matches up in some meaningful way. And then of course, check for data quality. Anybody that's dealt with data knows that dirty data is one of the only surefire things, and it's awful. So that's what we have Athena for. I talked a little bit about Athena, but this is what it looks like. Again, if you've ever used any sort of database IDE, you're probably pretty familiar with this. You've got kind of your tables on the left-hand side here. You've got a window where you can do editing. And then finally, you've got the output from whatever query you ran in the bottom. Again, just like Glue, just like S3, it's serverless. I don't need to provision or manage anything. There's not a spin up time. There's basically, under the hood, there's probably fleets of servers running that are just waiting to handle. I don't necessarily need to pay for them running that fleet of service. I just need to pay for my time actually using the service. So again, that goes back to partitioning and compression, so I can minimize that. So I got one last poll for you guys. So that kind of goes more along with this. So, Athena basically lets you use just regular ANSI SQL. It supports complex joins, nested queries, windowing functions. I can deal with complex data types like arrays and structs. Obviously, if I'm storing JSON data in my data lake, then I need to be able to query that using Athena. And then it does support that ability to the partitioning that's happening, whether we defined it or the Glue crawler defined it. It'll support that so that we can only query the data that we need. Hold on. My apologies. I've been doing immersion days since 9 this morning, so my voice is getting a little rough.
Hey, Dustin, could you maybe share after folks have a couple more seconds to answer, could you share the results so people can see them?
Oh, does it not necessarily do that?
If you just press share, then I think the rest of us could see them. I'm just curious because I want to see what everyone else is thinking.
Okay. I didn't realize that. I
Thank you.
thought that everybody just could see all the choices as they came up. Okay. I'll do that on the next slide. So,
Thank you.
yeah. So Athena is actually very familiar technologies, at least anybody that's, worked with some of this stuff in the past. Athena is actually built on Presto, which was a product that Facebook made a few years ago. And, it basically allows you to do in-memory distributed query engine against basically flat files. And then the Glue metadata store is basically the Hive metadata store under the hood. So let's see, I will end this and share results. So the majority said 2006. Did you copy paste this, Courtney? Maybe I just didn't do it right. The trick question then, the real answer was 1999. So nobody was allowed to get that right. Yet some relational databases like MySQL didn't support it until like 2018. So doesn't really matter if it's in the ANSI standard or not. Okay, so just an advertisement for Athena. It is pretty fast given the problem that's actually trying to solve. It is tuned for performance. It has multiple readers so that you can parallelize queries. Like I showed in that screenshot, the results are actually streamed to the console. Under the hood, this is all API driven though, so that's not necessarily what's happening. When I run a query on Athena, the results are actually dumped to another file on S3. The console just kind of hides that a little bit and just automatically puts that back to the console. And again, like I said before, we can improve our query performance by compressing our data, by partitioning, using columnar formats like Parquet. Those are all going to help speed up the Athena process. It's cost effective so long as you take those strategies when you're actually designing your data lake, because you pay by query. It is serverless, so you only pay for what you use. It's $5 per terabyte scan in S3. So again, the less data that we have to scan, the better. Whether that's through compressed data or through partitioning, that's how we can really reduce that. An interesting thing is DDL queries and failed queries are actually free, which is quite useful because sure, if I query a table and maybe I try to query a column on the table that doesn't exist, it's going to fail instantly. That's not really saving me any money. However, if maybe I've got a very complex query where I'm doing some sort of comparison between two fields in a table, and for the most part, their types align. But then all of a sudden, maybe there's dirty data, and I cannot cast something to something else that I want to do. So maybe it's been running for 3 minutes and it gets to that point in the query, it's going to fail. So instead of paying for that 3 minutes of execution, I end up actually just getting that query for free. So that's actually very useful. Again, we want to use compression. We want to use partitions. We want to use columnar formats.